Seema, and welcome to part 11 of the chapter States of Matter. We are continuing with our discussion of gas laws, and in this video I'm going to tell you about Avogadro's law. As I told you in the previous videos that there are four variables in the properties of gases when we study the properties of gases. The four variables are the number of moles, pressure, volume and temperature. When two of these are constant, the other two have a relationship between themselves, and this relationship is studied under the different gas laws. In the case of Avogadro's law, we call it the volume-amount relationship. The amount is given by the number of moles and V is the volume, which means these are the two variables which have developed a relationship between themselves. So pressure and temperature are the two properties which would be constant. So when pressure and temperature are constant, volume is directly proportional to the number of moles. This is basically Avogadro's law, that the volume is directly proportional to the number of moles when pressure and temperature are constant. Before I come to the statement of this law, I would like to explain this relationship. It's really easy to understand. If volume is directly proportional to N, mathematically, volume would be equal to, the proportionality constant K, and since this is the fourth law that we are doing, this would be K4 and N is the number of moles. The number of molecules in chemistry we studied as the quantity is studied as number of moles because the atoms are very, very small in size and the SI unit for it is the number of moles. So we use number of moles, I'll come to that later, but let us first understand this relationship. Volume is directly proportional to number of moles. If I start filling the balloon with air, if I blow a little, the balloon becomes bigger. So what am I doing to the balloon? I'm adding molecules of air to it as I'm blowing into it. The pressure is the atmospheric pressure, which is pressurizing the balloon from the outside, and the volume of the air inside will be balanced, or it would be fixed when the pressure inside the balloon is equal to the pressure outside. So when does that happen? In order for that to happen, the balloon starts expanding. As I add more molecules, the balloon expands. If I add still more molecules, what happens? If I blow still more, I find that the balloon expands still further. It expands even more. So we can see that as the number of moles or number of molecules is increasing, the volume is increasing. It's easy to understand this, that as the number of moles increases, the volume increases, provided the temperature of the room is constant. The temperature of the air inside the balloon is also constant. So the temperature and pressure, if they are constant, then as you keep on adding more and more molecules, the volume increases, and as you decrease the molecules, the volume decreases. Right? So this is one thing that is clear. This can be, usually it is explained with the help of this jar with a piston, right? And this is a piston. A piston is a lid that can go into a jar. It's a lid that seals very nicely into a jar, but instead of being outside and covering it from the outside, this lid can go into a jar that is straight. This is the best duplication that I could do. This is a glass and this is my camera lid, and I can imagine this to be a frictionless, a piston, right? A lid that moves inside the glass, and it moves inside the glass and it can go in. When will it go? When will it stop? In my case, it is not stopping because it is actually sealed nicely. It's loose, it's a glass and it's not straight. But in my case, it is stopping because it is touching the walls and it cannot go any further. But if you imagine this to be straight and you imagine there to be air inside the jar, if there was air inside the jar, the atmospheric pressure is pushing the lid downwards and the air inside the jar is pushing it upwards. When will it come and stop? It will stop at that place where the pressure of the atmosphere and the pressure of the air inside is equal. It's understandable. When does a tug of war, in a tug of war, nothing happens when the force with which you're pulling on both the sides is equal. So the force with which the atmosphere is pushing the piston down is equal to the force with which the gas is pushing the piston upwards. At that point, the piston balances in the jar. Now, let us imagine that this jar has an opening in the bottom. There is an opening here, and it is possible for me to, and this opening can be sealed. So whatever air was present, that was present, I can remove this and I can blow more air into the jar from the bottom. When I blow more air into the jar, what will happen? If the piston could not move, if the jar was sealed, and I added more air, I of course can add more air because air occupies the volume of the container. So if the volume of the container was fixed and the lid was tight here, I could have added more air. But now the lid is such that it can move, and it moves ever, it is very sensitive. So the pressure with which the atmospheric pressure is pushing the lid down, but when I put more molecules into the jar, what will happen? The pressure inside the jar will start increasing. Why will it increase? Because what is pressure? Pressure is the number of molecules of air or a gas that hit the walls of the container per unit volume. The amount of bombardments per unit volume is the pressure. In order to keep the pressure constant, now so that the pressure inside the jar is equal to the pressure, which is the pressure with which the air is pushing the lid upwards, should be equal to the pressure with which the atmosphere is pushing it downwards. In order to obtain that, what will happen? The lid will move upwards. When the lid moves upwards, or the piston moves upwards, the volume increases. And when the volume increases, the number of molecules of air per unit volume remains the same. So the number of molecules per unit volume remains the same. The energy is the same because the temperature is constant. So the number of bombardments remains constant, which means the pressure remains constant, or it becomes equal to the atmospheric pressure. So what happened when you added more molecules? In order to keep the pressure constant and at a certain temperature, the volume automatically increased. The volume automatically went up when you added more molecules, because in order to maintain the same pressure, the number of molecules per unit volume should remain constant. So when you're adding more molecules, the volume increases in order to have the same number of molecules per unit volume, so that you have the same number of bombardments in the jar. So the volume increases. So this is Avogadro's law. Now let us come to the statement of the law. The statement goes a step further. It does not just talk of this relationship. It goes a step further, and that is why I am talking of the statement after explaining this relation to you. Avogadro said that equal volumes of all gases under the same conditions of temperature and pressure contain equal number of molecules. He even specified that if you have the same volume of different gases at the same temperature and pressure, all of those, the same volume, that is 1 liter of this, 1 liter of this, 1 liter of this, 1 liter, all of them will have the same number of molecules. Isn't it beautiful? This was kind of combining Dalton's atomic theory too. And in the first chapter, you would have studied about the moles also, where I told you here we say volume is directly proportional to number of molecules, but number of molecules is in which unit? It is in moles. So now we come to the next part of the explanation, that is the mathematically how would we be handling this law. I hope you have now understood that equal volumes of all gases under the same conditions of temperature and pressure, they have same number of molecules. So volume is directly proportional to N, where N is number of moles. What is number of moles? When we talk of a dozen of something, a dozen bananas, we mean the number dozen, or the term dozen means 12. Right? It means 12. Similarly, a mole is actually a certain number. and that number is 6.022 into 10 to the power 23. 1 mole of any substance contains 6.022 into 10 to the power 23 particles of that substance. If I say 1 mole of oxygen molecules, it means it is 6.022 into 10 to the power 23 molecules of oxygen. If I say 1 mole of electrons, it means it is this number, 6.022 into 10 to the power 23 electrons. If I say it's 1 mole of hydrogen atom, it means it is 6.022 into 10 to the power 23 atoms of hydrogen. So, mole, just like a dozen, is a specific number of the particles or the entities that we are talking of. So when we say volume is directly proportional for all mathematical problems, we will take n to be the number of moles. So your questions, numerical problems would be in terms of number of moles. If they are in terms of number of molecules, or they give you the mass, you have to calculate the number of moles and then arrive at your answer. So we say 1 mole is a certain quantity. How did we come to this? How did we arrive at this? Not really related with this topic, but let me just tell you that carbon, the isotope of carbon, that is carbon 12, it weighs 12 grams of carbon is the molar mass of carbon. And the number of molecules, atoms of carbon that are present in exactly 12 grams of carbon is known, that number is known as 1 mole. And that number comes out to be 6.022 into 10 to the power 23. That is how this unit was determined or fixed. So anything after that, now we believe that anything that has 6.022 into 10 to the power 23 particles, it means it is 1 mole of that substance. Having understood that, now when we say 1 mole, when we say that equal volumes of different gases have same number of molecules, then we would say if we have 1 mole of different gases, then 1 mole of different gases at the same temperature and pressure should have the same volume. When we are saying that equal volumes have the same number of molecules, then 1 mole of every substance at the same temperature and pressure should have the same volume, because after all they are directly related. So this statement can be reversed or understood that 1 mole of any gas should have a fixed volume at a fixed temperature and pressure. We know that number of moles, if in a question you're given the mass of the substance, then how would you calculate the number of moles? We know number of moles is equal to the given mass divided by the mass of 1 mole, which is known as the molar mass of the substance. Right? Mass over molar mass gives you the number of moles. For example, if you want to calculate the number of moles of oxygen, and you've been told that you have, let us say, 64 oxygen molecule. You have 64 grams of oxygen which has been given to you. So we'll write 64 grams divided, what is the molar mass of oxygen? The molar mass of oxygen is 32 grams. So we'll say 64 upon 32, that is the molar mass, will give us the number of moles. The mass given to us is m, and the mass of 1 mole is this much. So if we divide the mass given to us by the mass of 1 mole, we will get the number of moles. So number of moles, we get 64 grams of oxygen is given to us, and if we divide it by 32, it means we have 2 moles of oxygen molecules. So that is how you would calculate the number of moles if you get it in a problem. Now, why are we thinking of this? Because sometimes you can even relate density to this. How would that be? Now we know that volume is equal to K for N. And if we substitute the value of N here that we calculated here, mass over molar mass, then V would become equal to K for mass over molar mass. Or, in order to get density, what is density? Density is mass per unit volume. So molar, if we take this here and bring volume down here, then M becomes equal to K for molar mass, small mass. It will not be molar mass. The total mass given to you upon volume. Yeah? Yes. So molar mass would be equal to K4 m over V, where m over V, the mass of the substance divided by volume, is density. So we can also say that V is equal to K4D. These are just a little changes made for your numerical problems. Now it is important to remember when we say that 1 mole should have a fixed volume, then we would like to know, is there such a standard that we already know of? The temperature and pressure should be constant. So these temperature pressure conditions which are constant, that is which we believe are normally constant, for all scientific studies, we fixed a certain temperature and pressure. That is known as the standard temperature pressure. So under standard temperature pressure conditions, what would the volume of 1 mole of any gas be? First of all, we should know what is standard temperature and pressure. The standard temperature for STP or standard temperature pressure conditions, the temperature at STP is 273.15 Kelvin, which is 0 degrees Celsius, or the freezing point of water, or you could call it the melting point of ice. So the temperature at STP, the standard which we believe is 273.15 Kelvin, and the pressure at STP is 1 atmosphere. 1 atmospheric pressure is equal to 10 to the power 5 pascals. So whenever you're using STP conditions, the temperature is 273.15 and the pressure is 1 atmospheric pressure, and you're carrying out the measurements under those conditions. And we find that if we take 1 mole of a gas at standard temperature pressure conditions, its volume would be equal to 22.4 liters per mole. And now this holds true for all the gases. All gases should have a volume of 22.4 liters per mole at STP. That is at 273.15 Kelvin and at 1 atmospheric or 10 to the power 5 Pascal pressure. There is another standard that sometimes is mentioned, which is known as the standard ambient temperature and pressure conditions. 0 degrees Celsius is not room temperature. So you'll have to freeze, you'll have to cool down and carry out your studies at that temperature in a refrigerator or in a cooled place. So instead, this condition was now, it's more practical. The standard ambient that usually we believe a room is at about 25 degrees Celsius. So the temperature at SATP is 298.15 Kelvin, which is 25 degrees Celsius, and the pressure is taken as 1 bar. Sometimes we use and 1 bar is slightly different from 1 atmospheric pressure. And therefore, the volume of 1 mole of any gas at SATP conditions, that is the standard ambient temperature and pressure conditions, turns out to be 24.789 liters per mole. So we find that the volume at STP and volume at SATP are different. You will have to memorize all these the conditions and what are the volumes at STP and SATP for your numerical problems. Now there is another problem, I'm now introducing the concept of ideal gas. At STP, the volume of an ideal gas should be equal to 22.7 liters per mole. But gases are not ideal. I am a teacher, but I'm not the ideal person. No one can be absolutely perfect. Similarly, gases cannot be absolutely perfect, which means that do I follow all the rules? Am I really am I just perfect 100%? I may be lacking here. There may be a little faults there. So nothing in the universe is perfect. So similarly, these molecules also, I would like to bring back my example of children in a playground. The molecules of gases are like children in a playground. And when we talk of the pressure of the gas, we say it is the number of times, the number of bombardments of the molecules on the walls of the container. So there are children who are playing in the playground and they are coming and touching the boundaries of the playground which form the pressure. Is it possible that children only come and hit the walls of the or come and touch the boundaries and they do not interact with each other? Is it possible? When you are in the playground, you might have a fight with a kid, you might like another one, you might be attracted to a third one. So there are other interactions which are going on. It's not just bombardment with the walls of the container. That is, molecules will not bother about the other molecules. Children in a playground will not look at other children. They will only go to the corners and they will go and hit the boundaries. That never happens. So this is what Charles' law, Boyle's law and Avogadro's law, they assume children to be ideal, which is not possible. So the molecules of gas are not ideal. They are not oblivious to the presence of other molecules of gas around them. They do react, they do interact, they might get attracted, they might go and accidentally hit another molecule, and that may affect their speed, that may change their direction. So gases are non-ideal. But at STP, the molar, therefore, this volume that we get is not of an ideal gas. If the gas was ideal, then at STP conditions, the volume should have been equal to 22.7 liters per mole. But ideal gases do not exist. Ideal kids, ideal human beings, ideal everything, ideal universe. There's nothing ideal in this world. So ideal gases do not exist, and what we have are real gases. We'll come to that concept in a later video. So this was all about Avogadro's law, and if you found my video helpful, please give it a thumbs up, and I would appreciate that. Subscribe to my channel, share the videos with all your friends, and please help me to spread information about them, about their existence, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.